So now let's discuss properties of matrix transformations. So properties of matrix transformations. So let's let A be an n by m matrix. I'm going to use A now, so you can't confuse little m and big M. And I will denote elements, will denote elements in Rm by the symbol, by ordinary vector notation. So, but of course it's a point in Rm, so that really means it's a list of m numbers, and we're supposed to be thinking about them as being these columns. But it just symbolically, I'll just write it as a vector. So I'll just write the symbol u, or v, or whatever, but with a little arrow over it. So, so u is that, v, for example, would be like v1 up to vm. Okay, and that's just some notation, so now let's talk about some of the properties. So the first property is that Ta of the 0 vector is equal to the 0 vector, but here, this here is the 0 vector in Rm, so that means that this is really 0, 0. It's a bunch of zeros, but you have m of them, and then the output 0 vector is the n-dimensional. So this 0 vector, this is actually in, this is in Rn, so this one is equal to 0. It's a bunch of zeros, but now there are n of them, okay? And that is just immediate, because that's how matrix multiplication works. So the proof is very simple. I'll just outline the proof. So this is true. This is because if you take any matrix of all zeros, A times a 0 matrix is just equal to a 0 matrix. Always. So, by definition, Ta of the 0 vector is A times the 0 vector, and so that has to be the 0 vector, where vectors are special types of matrices. Okay, so that's the first property. It's not that surprising. Second property is that if you scale, so if k is a number, your vector v, so v is a vector, and then k is a number, so this is a number, so k is a number, and v is a vector, or a point, it's the same thing as a point in Rm. But anyways, we can scale points, so that means that the entire thing in parentheses is actually itself a vector. So this whole thing is still a vector, is still in Rm, just so we're all on the same page. But anyways, so you can input a bunch of coordinates, and then what happens if you multiply all those coordinates by the same number? How does that affect the output? And that's what property 2 says. It says that this output is just equal to the number k times the output when you just apply it to v. And again, that is just, why is that true? That is just because properties of matrix multiplication. So maybe I'll put a little bubble around these because you can ignore that. So So 1 is because of that. 2 is just, by definition, Ta of k times v is by definition a times kv, and properties of matrix multiplication say that's the same thing as pulling out the k. So you have to understand everything is different. K is a number, A is a matrix, and V is a vector thought of as a matrix. And of course, by definition, that's k times Ta of V. So that proves 2. So these all just follow from ordinary properties of matrix multiplication. And the last property is that if you add two vectors together, which of course gives you a new vector, then you can input that new vector into the function. So this whole thing is still a point in Rm, using the addition of points in Rm. And so in particular, you can take this summation of 2 points, and that gives you a new point, and you can input that into this transformation. And what that spits out is the summation of plugging in just the first one and plugging in the second one. And I just want to remark that because of property 2 here, the same holds if we subtract them instead. So it also holds if you subtract them. But why is that true? So 3 is simply because, again, that's just how matrices work. Ta, matrix multiplication, satisfies the distributive property if you add or subtract matrices. So remember, vectors are special types of matrices. By definition, this is just matrix multiplication of A with V plus U. And matrix multiplication is distributive. So that's A times V plus A times U. So by definition, that's just the transformation applied to V plus the transformation applied to U. So again, these 3 properties are just results of ordinary properties of matrix multiplication. So here's the first property, that these functions, if you input 0, they spit out 0. They behave well with respect to scalar multiplication. So this is all about how it deals with scalar multiplication by the number k. So k is a number here, as I previously observed, and it behaves well with respect to addition and subtraction of inputs. So these are the 3 properties of these transformation matrices.